In Ukraine's war with Russia, control of the sky at very low altitude has become one of the most decisive factors shaping daily combat along the front line. Military analysts and Ukrainian commanders increasingly describe small, unmanned aerial vehicles as a system that determines how troops move, how supplies are delivered, and how quickly positions are discovered and struck. The presence of reconnaissance drones above the battlefield can turn routine actions into immediate targets, often without soldiers on the ground realizing that they have already been observed. The transformation is driven by the widespread use of relatively inexpensive unmanned aerial vehicles that provide real-time surveillance and targeting information. While long-range missiles and one-way attack drones remain a major threat to cities and infrastructure far from the front, the immediate danger near trenches and defensive positions is often created by smaller reconnaissance drones and FPV strike platforms. These systems enable forces to identify vehicles, troop movements, and radio activity within minutes and link that information directly to artillery strikes or drone attacks. Among the most widely used reconnaissance platforms is the Orlan-10, a mass-produced fixed-wing UAV used by Russian forces for battlefield observation and targeting support. The system operates as a mobile surveillance platform, capable of detecting heat signatures, movement, and equipment from a distance using electro-optical and infrared sensors. Because Orlan-10 drones are frequently deployed alongside artillery units, the data they gather can be transmitted quickly to fire control systems, shortening the time between identifying a target and striking it. This shortened targeting cycle has become a defining feature of the conflict. Military observers note that even brief pauses by vehicles or short radio transmissions can lead to artillery fire once a drone has identified a location. For frontline units, the destruction of a reconnaissance drone can therefore have an impact beyond the immediate tactical situation. Removing the surveillance platform can interrupt the enemy's targeting chain and temporarily disrupt the rhythm of artillery operations. The Orlan-10 platform also illustrates how reconnaissance and electronic warfare functions are increasingly combined. Some variants are equipped with the Lear-3 electronic warfare system, which can interfere with radio and cellular communications within an area of roughly 6 kilometers. In practical terms, this means the same drone that identifies a position can also disrupt communication between units, complicating coordination and slowing reaction times at critical moments. The result is a battlefield environment shaped not only by direct fire, but also by constant observation. Soldiers may remain undercover yet still feel exposed if a drone is suspected overhead, because they cannot be certain what information has already been transmitted to enemy forces. Analysts say this psychological pressure affects decision-making and movement patterns, often slowing operations and making units easier to track over time. Russia also deploys larger reconnaissance systems designed to extend observation beyond the immediate front line. The Forepost and Forepost-R platforms fall into this category and are described as medium-altitude, long-endurance drones derived from the Israeli Searcher Mark II design. These systems increase surveillance coverage across broader areas and, in some variants, are capable of carrying small laser-guided munitions. The addition of strike capability allows certain reconnaissance drones to transition directly from observation to attack when a time-sensitive target appears. Below that higher surveillance layer, Russian forces employ numerous shorter-range drones intended to monitor the near-rear areas of the battlefield. Systems referenced in open reporting include the Zastava, based on the IAI Bird-Eye 400, the Tachyon flying wing UAV associated with covert operations, and the Zala 421-16E5HD fixed-wing drone, often used for reconnaissance tasks. Their individual specifications vary, but their combined presence increases the density of observation across contested areas. This network of drones is used to locate armored vehicles, artillery systems, communications equipment, and electronic warfare platforms. It also focuses on identifying the operators and launch sites of Ukrainian drones, which are critical for maintaining local air awareness. When those operators are discovered and targeted, the protective drone screen over a sector can collapse, leaving ground units with far less information about incoming threats. Because of this environment, the contest between the two sides increasingly begins in the air before engagements occur on the ground. The ability to detect enemy drones early and remove them before they transmit targeting information has become a key requirement for survival along the front. Ukraine initially relied on relatively simple defensive measures against low-flying drones. Infantry units commonly carried pump-action shotguns and portable electronic warfare devices capable of jamming drone control signals. These tools provided a quick response when a quadcopter appeared suddenly at low altitude. A jammer could disrupt the connection between the drone and its operator, causing the aircraft to lose control, drift away, or return toward its launch point. In close-range situations, shotguns could destroy a drone during an attack approach. However, these methods revealed limitations as the scale of drone activity increased across the front line. Their effective range is limited, and maintaining sufficient coverage across hundreds of miles of active combat positions requires large numbers of devices and trained operators. As drone operations expanded, Ukrainian planners began searching for methods capable of providing broader protection while remaining inexpensive enough to deploy widely. This challenge became even more pronounced as the overall length of the contact line expanded. By September 2025, Ukraine's top military commander, General Alexander Syrsky, stated that the line of contact had reached approximately 800 miles, around 125 miles longer than the previous year. At the same time, Ukrainian forces were managing between 160 and 190 combat engagements each day, creating constant pressure across multiple sectors. Under those conditions, localized defenses such as handheld jammers could protect a trench or small section of terrain for limited periods, but they could not guarantee continuous protection along supply routes and rear areas. The combination of a longer front line and a growing number of daily engagements forced Ukrainian forces to reconsider how drone defense could be organized at scale. The search for a solution that is both effective and inexpensive has therefore become one of the central technological and tactical challenges of the war. Ukrainian engineers, military units, and defense programs are now exploring ways to build systems capable of countering enemy drones quickly, while avoiding the high costs and logistical demands associated with more complex air defense technologies. As the density of drone activity increased along the Ukrainian front, the limitations of early defensive methods became more visible. Portable electronic warfare equipment and small arms offered immediate responses, but could only protect narrow areas. Military analysts note that even effective jamming systems usually provide localized coverage rather than continuous protection across large operational sectors. In practical terms, a jammer capable of disrupting signals within 1 to 3 miles can shield a trench line or specific position, but supply roads, artillery sites, and nearby units remain exposed unless multiple systems operate together. According to estimates cited in the source material, analysts assumed roughly 2 to 4 kilometers of effective coverage per system under frontline conditions. Extending that coverage across the full length of the contact line would require hundreds of systems operating simultaneously. A rough estimate suggested that approximately 600 networked electronic warfare units would be needed to maintain consistent protection along the entire front. Each of these systems requires vehicles, batteries, spare components, trained operators, and reliable command links. Maintaining them under continuous combat conditions adds further logistical pressure. Cost has therefore become a central factor in the development of counter-drone defenses. Portable electronic warfare kits vary widely in price, ranging from roughly $500 to as much as $10,000 depending on capabilities. Many commonly used systems fall between $1,000 and $3,000 per unit. However, maintenance, damage, and constant replacement increase the total expense over time. Equipment may be lost due to shrapnel, mechanical failure, mud, or simple wear after extended use in field conditions. Shotguns, which became a widely discussed last resort defense against attacking drones, are significantly cheaper. The source describes new pump-action models typically costing between $200 and $350. Yet large-scale deployment still requires tens of thousands of units when distributed across multiple brigades and frontline sectors. More importantly, shotguns do not deny the enemy access to the airspace above the battlefield. They function primarily as a final defensive measure when a drone has already reached close range. As a result, Ukrainian forces began searching for methods that could intercept enemy drones earlier and more consistently. In 2024, the increased use of first-person view interceptor drones appeared to offer a breakthrough. Ukraine had already expanded production of FPV drones to extremely large numbers, with estimates suggesting output reaching into the millions each year. Many of these platforms cost only a few $100s, allowing commanders to deploy them rapidly in response to emerging threats. FPV interceptors changed the logic of air defense at very low altitude. Instead of relying only on static systems or handheld weapons, units could launch a drone to hunt another drone. These interceptors could be directed toward reconnaissance UAVs as soon as they appeared, potentially destroying the enemy's surveillance platform before it transmitted targeting data. In practice, the earliest interception methods were straightforward. Ukrainian operators frequently attempted to ram Russian reconnaissance drones with small quadcopters in order to damage propellers, break frames, or force them into an uncontrolled descent. Over time, operators added explosive payloads to increase the chance of destroying the target, even if the impact was not perfectly centered. The interceptor itself effectively became the weapon. This method provided immediate results and reduced reliance on longer targeting chains involving artillery or separate strike drones. However, the approach created a logistical problem because the interceptor was usually destroyed during the engagement. Military observers describe this situation as a drone-for-drone exchange, in which every successful interception still consumes equipment, batteries, and operator time. When reconnaissance flights occur repeatedly over the same sector, even a high success rate can lead to constant consumption of interceptor drones. In sectors with heavy aerial activity, defense can resemble a steady drain on resources rather than a one-time response. The challenge becomes more complex when the enemy adapts its flight patterns. Changes in altitude, routes, or timing can force defenders to launch multiple interceptors for each successful kill. Even when every engagement ends with an enemy drone destroyed, the number of sorties required to achieve those results affects how quickly supplies are depleted. Commanders therefore began seeking ways to intercept hostile drones without sacrificing their own aircraft in the process. One concept explored by Ukrainian developers involved mounting firearms, including shotguns, on drones. In theory, an interceptor drone equipped with a shotgun could fire at a target and return safely, allowing repeated use instead of a single destructive engagement. However, practical testing revealed significant limitations. Most drone-mounted shotgun configurations could carry only 1 or 2 shells before requiring a reload, which severely limited the number of engagement attempts. In addition, recoil from the weapon often destabilized the aircraft. Even minor imbalance during firing could flip the drone or send it into an uncontrolled spin, ending the mission with a crash. Engineers studying these experiments concluded that recoil management and ammunition capacity remained major obstacles for weaponized interceptor drones based on small quadcopter platforms. These limitations pushed Ukrainian developers to explore simpler mechanical solutions designed to disable enemy drones without destroying the interceptor itself. One of the concepts described in the source material is a device known as Aerotroll, developed by Ukrainian engineer Andriy Pavlovsky. Pavlovsky had previously worked on robotics projects for logistics support and bomb disposal during the war before shifting his attention to counter-drone technology as low-altitude UAV activity intensified. The Aerotroll system was designed specifically to address the 2 major problems identified in drone interception: the loss of the interceptor and the difficulty of recovering enemy drones for intelligence analysis. Instead of relying on explosives or firearms, the device uses a purely mechanical method to capture hostile UAVs. According to the source description, Aerotroll attaches to a standard quadcopter frame measuring approximately 10 to 15 inches across. The system contains no dedicated onboard electronics and can be installed quickly using basic ties or clips, allowing field units to adapt existing drones rather than relying on specialized airframes. The capture mechanism uses thin, high-strength vertical lines intended to tangle in the propellers of the target drone. When the propellers become entangled, the enemy aircraft rapidly loses lift and control. Operators then have 2 options. The device can be detached immediately, allowing the captured drone to fall, or the interceptor can tow the disabled UAV back toward friendly positions. Recovering the drone intact allows technicians to examine internal components, radio frequencies, and wiring configurations, providing intelligence about how opposing drone units operate and adapt. The system is also described as relatively lightweight, weighing just over 300 grams. This low weight allows the carrier drone to maintain flight stability and sufficient endurance during interception missions. Operators can make several passes at a target if the first attempt fails, which reflects the reality that drone interceptions rarely succeed on the first approach under field conditions. According to the source, Aerotroll units have been listed on Ukraine's Brave One Defense Innovation Marketplace at a price of about $18.50. Several hundred devices have reportedly been delivered to frontline units for testing, training, and development of operational tactics. Early use has included attempts to intercept reconnaissance drones and to neutralize fiber optic guided FPV drones placed along roads to ambush passing vehicles. These early deployments highlight how low-cost counter-drone tools are becoming part of broader efforts to protect logistics routes and gather intelligence. By capturing drones rather than destroying them outright, operators can obtain technical information that may influence electronic warfare strategies or help identify evolving enemy tactics. The development reflects a wider trend within Ukraine's defense sector toward inexpensive and rapidly deployable solutions. Engineers and military units are focusing on equipment that can be produced quickly, distributed widely, and repaired easily in frontline conditions. As drone numbers increase on both sides of the conflict, the ability to sustain defensive operations day after day has become a decisive factor shaping battlefield strategy. The appearance of low-cost counter-drone tools such as Aerotroll reflects a broader shift in the technological dynamics of the war in Ukraine. Military planners increasingly describe the conflict as an environment where innovation, production speed, and affordability often outweigh the advantages of more complex but limited systems. In a battlefield where thousands of drones operate across hundreds of miles of front line, maintaining a consistent defensive presence has become as important as achieving individual tactical successes. Analysts note that many counter-drone systems available on the global market rely on specialized launchers, proprietary components, or integrated radar and command networks. While these systems can offer higher detection ranges and more advanced targeting capabilities, they also introduce higher costs and greater logistical demands. Such requirements can complicate deployment across a long and constantly shifting front line where equipment must be moved, repaired, and replaced under combat conditions. By contrast, the approach described in the source emphasizes simplicity and scalability. Devices like Aerotroll are designed to operate with common quadcopters already used by military units. Because the device contains no onboard electronics and relies only on mechanical components, it can be assembled quickly and installed without specialized technical training. The system's thin capture lines are also described as difficult to detect visually at a distance, which can increase the chances of a successful interception before the opposing drone operator understands what is happening. According to the source description, early tactical results have suggested that small units equipped with such devices can achieve noticeable effects within limited operational sectors. In one reported case, a unit using Aerotroll was able to bring down a significant proportion of targets during a series of sorties, indicating that low-cost equipment may be capable of altering local drone activity patterns. Military observers note that when reconnaissance drones begin to face repeated losses, operators may become more cautious about launching them into contested airspace. This dynamic introduces the concept of cost-to-kill ratios as a strategic factor in drone warfare. If expensive reconnaissance platforms or specialized drones can be neutralized by devices costing less than $20, the economic balance of aerial operations can shift rapidly. Each interception increases the financial and operational risk associated with launching additional drones, potentially reducing the tempo of enemy reconnaissance flights over contested areas. At the same time, Ukrainian officials and analysts acknowledge that technological advantages in the drone war are often temporary. Russia has repeatedly adapted its systems by modifying flight altitudes, changing routes, or introducing countermeasures designed to defeat existing defenses. Similar adaptations could potentially reduce the effectiveness of capture-based interception systems if propeller guards, new flight patterns, or decoy drones are introduced. Because of this possibility, the long-term effectiveness of Aerotroll and similar tools will depend on how quickly production can expand and how rapidly frontline units can adapt their tactics. The source states that individual devices can be assembled quickly, with one person reportedly able to produce several units in a single day. However, achieving meaningful coverage across large operational sectors would require moving beyond small-scale assembly toward more organized batch production. Another factor shaping future development is the potential for design modifications that expand the device's role beyond interception. According to the source description, the same platform concept has been discussed as a basis for additional variants capable of carrying small explosive payloads. Such versions could be used for tasks including mining approaches, targeting communications equipment, or striking exposed infrastructure such as antennas or weapon barrels. If implemented, these changes would transform the device from a single-purpose interceptor into a multi-role tool capable of performing both defensive and offensive tasks. These discussions illustrate how quickly drone-related technologies evolve under wartime pressure. Ukrainian defense programs have increasingly focused on solutions that can be produced in large quantities using widely available components. The goal is to ensure that defensive measures remain sustainable even as the scale of drone activity continues to expand. The strategic challenge is defined by the size of the battlefield. With a contact line stretching hundreds of miles and daily combat engagements numbering in the hundreds, maintaining continuous aerial awareness is essential for both sides. Reconnaissance drones guide artillery, monitor logistics routes, and identify opportunities for attack. Countering those drones therefore becomes a prerequisite for maintaining freedom of movement on the ground. Military experts emphasize that the outcome of this competition will depend not only on technological innovation, but also on the ability to sustain production and training over time. Operators must be trained to detect enemy drones quickly, coordinate intercept missions, and recover captured equipment for technical analysis. Intelligence gathered from recovered drones can reveal communication frequencies, electronic components, and software changes that influence future countermeasures. The continuing evolution of the drone war also raises broader questions about the role of inexpensive technologies in modern conflicts. As systems costing only a few dollars or tens of dollars begin to influence operations across entire sectors, traditional assumptions about military hardware may change. The emphasis shifts from singular high-performance platforms toward networks of simple devices deployed in large numbers. For Ukraine, this approach represents an attempt to offset numerical advantages held by Russian forces through creativity and rapid adaptation. By focusing on low-cost solutions that can be distributed widely across the front, Ukrainian units aim to maintain the ability to challenge enemy surveillance even in sectors with heavy drone activity. At the same time, analysts caution that every technological step forward is likely to be followed by countermeasures from the opposing side. Future changes in drone design, electronic warfare tactics, or flight behavior may alter the balance once again. As a result, the competition in the low-altitude airspace above the battlefield is expected to remain one of the most dynamic and rapidly evolving aspects of the conflict. For now, the development of tools like Aerotroll demonstrates how engineers, soldiers, and defense programs are attempting to address a central problem of the war: how to protect troops and logistics routes from constant aerial observation while operating along one of the longest active front lines in modern Europe. The ability to intercept, recover, and study enemy drones may provide both immediate tactical advantages and valuable intelligence that shapes the next stage of counter-drone warfare.